there you are. So our next topic is coordinate vectors, and I'm going to start with a couple of prerequisites, tiny little theorems, and then we're going to give examples, and then we're going to give one more theorem. And the point is that this is a bit confusing. I know this specific topic is slightly confusing, and you'll see why in a minute. So here's a theorem. This is not confusing. This is very easy. V is a vector space. B equals V1, V2 through Vn is a basis. So this automatically implies that we're looking at a finite dimensional vector space whose dimension is n, right? And the statement is then any element v in V, any vector in the space, can be written as a linear combination of V1 through Vn. That's obvious. That's the definition of being a basis, of being a spanning set. But the important word in this theorem is can be written uniquely as V equals alpha 1 V1 plus alpha 2 V2 plus alpha n Vn. Okay, so if you take a basis, any element can only be written in one specific way. One specific way means there's a specific, unique choice of alphas that enable you to write many of which can be 0, for example. Okay, so you don't necessarily need all of these, but a way of saying that in order to write V, I don't need V2 is take alpha 2 to be 0, right? But there's only one way to do it if it's a basis. Okay, so let's prove this. Prove. Let's assume that there are two ways and show that they're in fact the same. Okay, so assume that V equals alpha 1 V1 plus dot 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 plus alpha n Vn, but is also equal to beta 1 V1 plus dot 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 beta n Vn. Assume that we wrote V in two different ways. Let's show that alpha I equals beta I for every I. Okay? So if this equals this, I can move everything to the left side. This is an equation. I can move everything to the left side, and I would get alpha 1 minus beta 1 V1 plus alpha 2 minus beta 2 V2 plus alpha n minus beta n Vn. That's what I get when I move everything to the left-hand side. Do you agree? And what's left on the right-hand side? 0. Do you agree? But look, this is a linear combination of the VI's, which equals 0. The VI's are a basis. In particular, they're linearly independent. If you have a linear combination of linearly independent elements that give 0, all the coefficients are 0. That's the definition of being linearly independent. Therefore, alpha I minus beta I equals 0 for every I. Do you agree? Because of linear independence. So maybe we should add here that the justification for this step is that B is linearly independent, because B is a basis. And therefore, alpha I equals beta I for every I. Good, everybody? So, if you have a basis, there's a unique way of expressing every element in the space in terms of a linear combination of the basis elements. Okay? So what's unique here is the alphas. Every V comes with n tuple of alphas that represent it with respect to the given basis. If you take a different basis, there are going to be different alphas. Okay? Good. So, this theorem is the foundation for this definition. So, V is a vector space, B is a basis. If V is alpha 1 V1 plus dot 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 plus alpha n Vn, then alpha 1, alpha 2 through alpha n, the coefficients, the scalars in that presentation of V as a linear combination of the basis elements, are called the coordinates of little v with respect to B, to that specific basis. Okay? And the notation is the following. We take V, the vector, and its coordinates with respect to the basis B are denoted like this. And this is merely the vector, and we usually write it as a column vector of those coordinates, alpha 1, alpha 2, through alpha n. And this is called the coordinate vector. Okay? Let's do some examples. So here's a first example.
Is it capital?
This is little v. It's the representation of little v with respect to the basis B. So here's an example. Big V is going to be R3. That's the vector space we're working in. And B is going to be the standard basis. 1, 0, 0, 0, 1, 0, and 0, 0, 1. Good? And V, little v, is going to be the vector 1, 2, 3. Okay? So what are the coordinates of V with respect to this basis B? So V can be written uniquely as these elements. Let's call the basis E rather than B. Please change that. And let's call this E1, E2, and E3. That's kind of standard for, I don't want to write it too close so you don't think that it's a new coordinate. So let's call this E1, E2, and E3. This is rather standard notation for the standard basis, so I'm going to use that. So V is 1 times E1 plus 2 times E2 plus 3 times E3. Do you agree? 1 times this plus 2 times this plus 3 times this. Do you agree? So, therefore, the coordinate vector of V with respect to this standard basis E is the alphas, 1, 2, and 3. So it's merely 1, 2, 3. And you're going to say, huh? What did we just do? V was 1 to 3 to start with, and now V is 1 to 3 again. It seems like we did nothing, and the reason is that this is the standard basis. If you're looking at the standard basis, well, really, you're almost doing nothing, okay? But if we take a different basis, so this will be example 1. Let's take example 2. V is still going to be R3, but now let's take a different basis. Let's call it F, and it's going to be the basis that we had before, exactly. 1, 1, 0. We discussed this in 3 or 4 lessons ago, we had this basis for R3. And we showed that it's indeed a basis. We actually proved that, first we showed that they're linearly independent, and then we showed very explicitly how to write a general vector ABC as a linear combination of these guys. And the coefficients were a plus b plus c over 2, a minus c plus b over 2. Remember that? I'll remind you of the details in a second. So this is a basis. And we're going to take the same vector. V is still going to be this 1, 2, 3 dude. So we have seen that V can be written, 1, 2, 3, can be written as 0 times 1, 1, 0, plus 1 times 1, 0, 1, plus 2 times 0, 1, 1. And the reason I'm saying we have seen that is because we actually calculated it explicitly. Let me remind you here. We saw that any vector ABC can be written as A minus C plus, let me write it, A minus C plus B divided by 2 times 1, 1, 0. And for 1, 2, 3, you get just 0. Okay, you can calculate it. Plus C minus B plus A over 2 times 1, 0, 1. Plus B minus A plus C over 2 times 0, 1, 1. That's in general. Okay? Does this ring a bell? Do you recognize this? Okay? Okay, good. So this is V, now written as a linear combination of these three guys. Let's call them F1, F2, and F3. Okay? So what are the coordinates of V with respect to the basis F? Okay, so let's write it here. I don't want to take a new board for it. Okay, so the coordinates of V with respect to the basis F are 0, 1, 2. Good? Clear? And it's confusing because 0, 1, 2 is not the same as 1, 2, 3. Those are different vectors. But the coordinate vector of V with respect to this basis is 0, 1, 2. All it means is that V can be written as a linear combination of F1, F2, and F3 using these coefficients. That's the coefficient vector with respect to this basis. Good? Clear? Okay. And now there are a few statements. And the first few are very, very straightforward. And I'm going to leave them as exercises. You can really first try them out on maybe an example or two and see that you believe them, and then try proving them. Okay, they're very straightforward, nothing sophisticated. So, theorem, but it's calling it a theorem is very paying a lot of respect to something very basic. If you take two vectors, v1 and v2, add them, and then look at what is the coordinate vector with respect to some basis b, that's going to be the same as taking the coordinate vector of v1 with respect to b plus the coordinate vector of v2 with respect to b. Okay? Makes sense? Requires proof. Okay? And the proof would be by saying what this means. This means that v1 is alpha 1, let's call the elements of b little b's. Okay? So v1 is alpha 1 b1 plus dot 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 alpha n bn. And v2 is beta 1 b1 plus beta n vn. And v1 plus v2 is alpha 1 plus beta 1 v1 plus alpha 1 plus, so you can, that's the proof, that's it, right? If what I said compiled, then spell it out. If it didn't, then you need to think a bit more, but then you'll understand it. Okay, very basic. So this is part 1 of the theorem. Part 2 of the theorem, if you take a scalar multiple of a vector and ask what is its coordinate vector, it's just going to be alpha times the coordinate vector of the original. Okay? And the third mini theorem here is that the coordinate vector of v with respect to b is 0 if and only if v was the 0 vector. That's the only vector whose coordinates with respect to any base are 0, 0, 0, 0, 0. Right? That also makes perfect sense. You need to spell out the details in order to prove it. Okay? Does everything here seem logical, seem reasonable? Okay? Without proofs, without the formality of proofs. Okay. And so proof, exercise, not hard.
So according to what you said, proving, for example, 1 is just writing what's given to us.
I said it. I want you to actually write it. Okay? I don't want to say it with more details and then you need to... When you approach a theorem and want to prove it, a very basic theorem, all you have is the definitions. So look at the definition, see what does this mean? What does this mean and why they're equal? And it'll just be the proof. Okay? Okay. So here's the theorem that I'm really interested in, which is going to be a consequence of this, but let's take a new board for it. For example, this one. So the statement is going to be that what you're doing when you're taking a coordinate vector, you're translating the vector into a different language. Instead of thinking of it as 1, 2, 3, you're thinking of it as 0, 1, 2. You did some translation, okay? And that translation preserves the property that we're most interested in, the linear independence, okay? And that's this theorem. So, and I'll write it and then prove it and then tell you why this is so important, why this is so useful. So, dim v equals n, b is a basis, then a set of elements v1, v2, up to vk, a set of elements is linearly independent. These are just k elements in V, if and only if the set of their coordinate vectors is linearly independent. V1, B, V2, B, up to Vk, B is linearly independent. That's the theorem. Let's think for a moment. Where do these guys live? Where does V1, V2 up to Vk, where are they taken from? V, right? So this is a subset of V. Do you agree? Where do these guys live? Where does this coordinate vector live?
Also in V.
No. In fact, the examples that I gave could suggest, falsely suggest, that these guys are also just vectors in V. Okay? But if you think, for example, of, let's say V is 2 by 2 matrices. Okay? And then these guys are all little 2 by 2 matrices. Okay? And writing them as a linear combination of the basis, let's say we're taking the standard basis for the 2 by 2 matrices, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, no, 0, 0, 1, 0, and 0, 0, 0, 1, then the coordinate vector is the alphas, right? These are still going to be column vectors. They're no longer going to be 2 by 2 matrices. Do you see that? They're just going to be columns listing the alphas, which are the coefficients. Do you see that? Okay. Let's add another example right here. Here on this board. Please look here a second. Here's another example, quickly. V equals 2 by 2 matrices over R. Okay. E, or let's call it B now, so we're precisely in B is going to be the standard basis, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. And let's take the matrix, let's call it V, let's not call it V, let's call it A, is going to be the matrix 1, 2, 3, 4. What is the coordinate vector of A with respect to the basis B?
1, 2, 3, 4.
Right, but it's a vector. 1, 2, 3, 4. Because A is 1 times this, plus 2 times this, plus 3 times this, plus 4 times this. Do you see that? So the coordinate vector, disregarding where A itself came from, what was the original V, the coordinate vector is always going to live in F, whatever the field is. In this case, the field was R. In F, in this case, let's say R4. And in general, back to this board, this thing is linearly independent in F, which was the general field, to the N. Do you agree?
The main dimension.
Okay, N is the dimension of the vector space. Do you agree? So this is important. We're translating any vector space into Fn. Good? And that's what we did all the times when we straightened polynomials into rows of matrices and straightened little matrices into row vectors in a big matrix. That's what we were doing. And this is the theorem that justifies that being linearly independent as rows of a big matrix is the same as the originals being linearly independent. Do you understand that? Okay, this is very, very important. We have been using it already. Okay, and this is hinting to that word that I mentioned earlier of isomorphism that we're going to reach very soon, of saying that 2 by 2 matrices over R and R4 are essentially the same vector space. Okay, in this sense. Okay, let's prove this. Proof. So there are 2 directions to prove here. One is that if these are linearly independent, then so are these. And the other is that if the coordinate vectors are linearly independent, then so are the originals. Okay, so let's start by proving this direction. So assume the vectors are linearly independent. Okay, so we're assuming that these are linearly independent. We want to assume that these are. We want to prove that these are. How do we prove that they're linearly independent? Take a linear combination of these guys that equals 0. Show that all the coefficients are 0. Okay, so take alpha 1 v1 b plus ... alpha k vk b equals 0. Take a linear combination of these guys that equals 0. we need to show that all the alpha i's are 0. Everybody with me? Everybody following the logic? I took a linear combination. I want to show that they're all 0. Now I'm going to use that exercise theorem, the lemma, in order to say that alpha 1, the alphas can go into the coordinate vector. That was part 2 of that previous theorem. And then adding can join up also inside the coordinate vector. So this means, I'm looking at this, right? I'm looking here. The alphas can be absorbed into the coordinate vector, and then the addition can be absorbed into the coordinate vector. That's what I'm using. So this means if the linear combination of these guys is 0, then alpha 1 v1 plus alpha 2, let's use the dot, 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 plus dot, 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 alpha k vk coordinate vector is 0. This is by 1 and 2 of the previous theorem. Do you agree? But then by 3 of the previous theorem, if a coordinate vector is 0, then the vector itself is 0. Right? And if the vector is 0, we're assuming that it's a linearly independent set that we started with. This implies alpha 1 equals alpha k, and they're all 0. This is since v1 through vk are linearly independent. Good? Okay. Notice that there's a difference between this 0 and this 0. This is the 0 in Fn. This is the 0 column vector. This is the 0 in the original V. Right? This is the 2 by 2 matrix 0. Good? Okay. How are we doing in terms of time? Good. We have time to do the other direction. So now I'm going to assume that the coordinate vectors are linearly independent. Does everybody see that what we proved is linearly independence of these guys? Right? We took a linear combination that equals 0 and showed that all the coefficients have to be 0. That's the definition of linear independence. Good? You don't seem happy.
No, it takes time to...
That's fine. But is there anything concrete that's... Okay. Okay, no, I agree. It takes time. It takes time to absorb. Let's do the other direction. I'm going to assume these guys are linearly independent. I want to show that these guys are linearly independent. So let's do that. In some senses, this course is not a hard course. Okay, it's not difficult. But what is challenging is the absorbing part, is starting to feel very comfortable with all the definitions. And when you say linearly independent, you mean take a linear combination that's 0, all the coefficients are 0. And doing that in your brain, when you see the term, that's what requires getting used to. That's the absorbing part. Okay? Once you do that, it's, in my personal opinion, much easier than calculus, for example. Okay?
Everything is much easier.
You agree?
Even diamonds.
Diamonds are easier than calculus? Oh, yeah, but that in English there's the word difficult and the word hard, and you can't ask for a difficult boiled egg and things like that. You have to be careful. Okay, so what are we proving now? We're proving the other direction. So now we're assuming that the coordinate vectors are linearly independent, and we want to prove that the original vectors are linearly independent. In fact, this is the direction we were using all the time, right? We translated to coordinate vectors as rows in a big matrix. We checked linear independence, and we deduced that the original polynomials or matrices or whatever were linearly independent. This was the direction we were using, right? Okay, so now we're assuming that the coordinate vectors, and we want to prove that the originals. So alpha 1 v1 plus alpha k vk equals 0. So take a linear combination of the original vectors, which equals 0, let's show that all the coefficients are 0. So if the linear combination is 0, then by 3 of that exercise theorem, the coefficient vector, the coefficient vector of this is 0 as well. Do you agree? That was exactly the statement in part 3, right? Look here a second. If you're looking at the 0 vector, its coefficient vector is 0, right? And now we have the coefficient vector of a linear combination. We can first separate it as a sum, and then each one pull out the alphas. Okay, it's really reading the proof of the previous direction backwards. So let's write that. So by 1, this equals alpha 1 v1 b plus alpha k vk b. What 0 is this? This is 0 where? Fn. This is the 0 column vector, and this is the 0 in whatever v was, right? This is 0 in v, and this is 0 in Fn. Good? Okay, and now we can use 2 by 2 alpha 1 v1. Alpha k, coordinate vector of vk. And now our assumption in this direction is that if you have a linear combination of these guys, which equals 0, since they're linearly independent, all the alphas must be 0. And this is the assumption of this direction, which is that the v1b through vkb are linearly independent. And that's it. That completes the proof. Okay? Good? So, the point is, what you should think of when you think of coordinate vectors is that really this is the machine, this is the tool that enables us to take any vector space, basically, any vector space. Once we have a basis, we can translate that vector space to Fn. And do things in Fn where we know how to do things, for example, rows in a matrix, and all kinds of things that we know easily how to do in Fn. And, well, whatever is justified by theorems, like this theorem, for example, that tells you that being linearly independent gets pulled back to the original space. So you translate to Fn, this is the translation to Fn, you check linear independence here, that's what we did all the time, and you deduce linear independence in your original space, which could be a space of polynomials, or a space of matrices, or a space of many, many other things that you may encounter as vector spaces, okay, stemming from totally different worlds. The property pulls back. This property of linear independence. If you want to claim other things, you need to prove them. Okay, good, everybody? Okay, so this is the idea of coordinate vectors. We will mention them again. But for now, that's where we'll stop.